Alright guys, so in this lecture we are going to look at the PCH 421 past questions, and basically what we are going to look at here is acid and basicity and how they affect the biological activity of drugs. Right now we are going to answer past question on that. We have a question here that says use the following equation obtain the Henderson-Hasselbalch equation. Now the equation that was given to you is HA plus H2O to give us in a reversible reaction HA minus plus H3O positive. So what we are going to do is to write the equation again. What is the equation like? You have HA plus H2O. Now this is a reversible reaction, so you are going to have two arrows. You must indicate that. And then you are going to have, this is going to give us H3O plus this is going to give us H3O plus A minus. Any way you write it is actually very, very correct. It can be A minus plus H3O plus. It can be H3O plus A minus, whichever way you write it. Now, you must understand something here. This HA, what is the meaning? HA means an acid. Is that okay? Why this H2O here is acting as a base? Now, one thing you should know is that water can act as an acid and also as a base. Hence, water is termed as amphoteric. You may see something like that in OBJ. Water is termed as amphoteric because it acts as an acid and also as a base. Now, you have been told the different kinds of acid, or you've been taught the different kinds of acid. We said we have the Lewis acid, and then we have the Brewster-Lawrence acid, and then lastly we have the Van Arrhenius acid, all right, which are also called the Arrhenius acids. These are the three kinds of acids we have. Now, Brewster-Lawrence acid, you say they deal with what? Electrons. Hence, you call Brewster-Lawrence acid electron donor. Lewis acid as electron donor rather, not Brewster-Lawrence. Lewis acid as electron donor. Then Brewster-Lawrence acid, we say they are what? Lewis acid as electron acceptors. Sorry about that. Electron acceptors. Why Brewster-Lawrence acid as proton donor? All right. So anything that is capable of donating a proton is said to be a Brewster-Lawrence acid. Whilst anything that is actually receiving that proton will become a Brewster-Lawrence base. Now, one thing that you should know is that an acid here will form a conjugate base here at the product side, while a base here will form a conjugate acid at the product side. Now, in this case, if you look at this reaction very well, you agree with me that this HA here actually donated a proton to this, right? Look at it. This becomes H plus H2O. We give us what? H3O plus. Is that okay? Now, I told you that a base here, anything that is formed when that base receives a proton becomes what? The conjugate acid. So this here will become the conjugate acid. Is that okay? Now, the next thing you ought to look at now is this acid here that donated the proton, whatever that is remaining will become the conjugate base. Is that okay? So HA donated a proton, it donated hydrogen. So what is left here is what? A minus. So this one will become the what? Conjugate base. That is one thing that you should know. So something that was an acid here will become a base at this side. The one that was a base here will become what? An acid here. Now, the Henderson-Hasselbalch equation they ask us to actually prove states the relationship between the ionized form of a drug and the what? unionized form of a drug. Is that okay? State the relationship between the ionized form of a drug and the unionized form of a drug, and also relationship between the pH and the pKa of that drug. Now, how do we prove the Henderson-Hasselbalch equation? Now recall, the one that was given to us was Ha plus H2O. Told you that this is a reversible reaction. This is a reversible reaction to give us A minus plus what? H3O plus. And everyone that knows why this thing is like this. Now, HA is usually in aqueous form. H2O is in liquid. This is in aqueous. This is in what? Aqueous. When you see something is in aqueous form, it means it's actually something dissolved in what? Water. Right? Good. Now you are not going to write the dissociation constant because this thing actually dissociated. You are not going to write the dissociation constant or the acidity constant rather, Ka. Now the acidity constant is given by the law of mass action. Now what is the law of mass action say? Say you write the concentration of the reactant at equilibrium. This thing you see here is at equilibrium. So our dissociation constant or acidity constant is usually measured at what? Equilibrium. So what they actually do is you write the concentration of the reactant at equilibrium divided by the concentration of the product at what? Equilibrium. However, only aqueous gas can actually appear in the equilibrium constant expression. Only aqueous solution and gas can appear. Pure solids and pure liquid do not appear because the only things that actually appear are the ones that their concentration changes with time. Pure solid and pure liquid, their concentration do not change with time. For instance, if you put water somewhere and that water goes into a reaction, that water will still remain water because it's pure. The concentration of the water does not change with time. Is that okay? So general idea, just know that pure liquid and pure solid do not change in time, do not actually show in the equilibrium constant expression. The only thing that show in the equilibrium constant expression are what? Aqueous solution are what? Gas. Is that okay? So in this case now, what do you think will be the equilibrium constant expression? What I said earlier is that you write the concentration at equilibrium of the reactant divided by that of the product, but pure liquid must not show. So to write concentration, you usually put something like this, A minus. Is that okay? Bracket. Then this one will be what? H3O positive, bracket. These are aqueous divided by. Now you agree with me that the next thing you are going to have here will be what? HA. Water, H2O, is a pure liquid. From what I said pure liquid do not show in the what? Equilibrium constant expression. Is that fine? So what we have is this is the Ka. Now that you have gotten this Ka, what do you think we can actually do after getting this Ka? Is to make this H3O plus the subject of the formula. Are you getting it now? So next step, make H3O plus subject formula. Is that okay? Now if you make H3O plus subject of the formula, what are we going to have? This one multiply this, Abi. So you have this over 1 cross multiply. So what are you now going to have? You are going to have, first of all, let's multiply this side. So this is going to give us what? A minus, and then what? H3O positive times 1 will still be the same, Abi, equals to what? Ka bracket what? HA. Now, to get H3O positive to be at the reactant side or subject of the formula, divide both sides by what? A minus. So that when you divide both sides by A minus, this can cancel this. And then what you will be having will be what? H3O positive is equals to, now this will give us Ka There you have HA. There you have A minus. All right. Now that you have gotten this, the next step now is, after you have gotten this, the next step is to multiply through by logarithm, negative logarithm. Is that okay? The next step is to multiply through by what? Negative logarithm. So you can write multiply through by negative log. So if you multiply through by negative log, this is going to give us minus log H3 positive to give us minus log Ka bracket HA divided by A minus. This is what you do. Now, in mathematics, when you have something like this, one thing you can actually do, record that this Ka is like multiplying these two things, right? So you can actually put these ones here in brackets, since they are almost the same. They are concentrations. You can put times, it's still the same thing. Put these ones here in a bigger bracket and you say HA, are you getting it? Divided by what? A minus. Do you understand that? Good. Now that you've understood this step, the next thing that we now need to look at, note that this logarithm is also multiplying everything in this bracket. Now, at the end of the day, what are we now going to have? We are going to have minus log H3O positive is equals to, use this log now to open through. In mathematics, if you have log A times B, it's still the same thing as log A plus log B. Is that okay? If you have log A times B, it's still the same thing as this. So what I'm going to do now, this is going to give me minus log, here will be what? Ka. Use this minus. Told you that normally it's supposed to be positive in the middle, right? But because of this negative now, that positive will change to what? Minus. Is that okay? So here it becomes, or before we even, yeah, let's leave the minus outside so that some persons will not get confused. I told you that log A times B is log A plus log B, right? So it means log Ka times Ha over A minus will be what? Log Ka plus what? Log what? Ha all over what? A minus. Abi? Now, we can now use this minus to open through so that some persons will not get confused. So this will become minus log H3O positive is equals to minus log Ka minus log what? Ha all over what? A minus. Now, in chemistry, generally we are taught pH. You say pH is what? Negative logarithm of hydrogen ion concentration or hydrozonium ion concentration. Is that okay? So it means this whole thing here is equals to pH. Because say pH is negative logarithm of what? Either hydrogen ion concentration or what? Hydrozonium ion concentration. So in this case now, this will become what? Minus, it will no longer be minus log. This minus log is still the same as what? pH. So I'm going to have pH will be equals to pKa is also minus log Ka. So in place of this whole thing here, you put what? pKa. Is that okay? Then you have minus log Ha all over what? A minus. Now listen, there's a manipulation we have to do here. Now, if in mathematics, by logarithmic law, we want to make this side to be positive, we can do that by taking this one up and taking this one down and then putting minus 1 on top. Because minus 1 is like the inverse Is that okay? So pH now will be equals to pKa minus log. Instead of us having A minus over, HA over A minus, we are now going to have what? A minus all over what? HA. Raised to the power of what? Told you that in this case now, this will now be raised to the power of what? Minus 1. This thing is still the same as what we have here. Is that okay? So that at the end of the day, according to law of logarithm, if you're also good in mathematics, is say if you have log a raised to the power of n, you bring the n backwards, so this becomes n log a. So this is log this raised to the power of minus 1. The law says bring this on what? Backward. So that at the end of the day, pH will be what? pKa plus log what? Final answer A minus all over HA. So for most times, when they say write the Henderson-Hasselbalch equation, this is what you are going to write. Are you getting it now? Henderson-Hasselbalch equation. This is what you are going to write. pH is equals to pKa plus log A minus all over HA. Where A minus is the dissociated ions or the dissociated drug, and HA is the what? Undissociated drug. Is that okay? So pH is equals to pKa plus log of dissociated ion all over undissociated ion of the drug. Is that okay? So that is that. Now, the next question. So that is that for this proof. We are done with this one. The next question says, calculate the average percentage of aspirin that will be in the ionized form in the stomach after oral administration of 300 milligram of single dose. Now, let me give you other formula. Now, from this equation, they were able to manipulate some equations that are very, very key. Now, when they say percentage of ionized drug, what do you think they mean? They mean what? A minus, Abi, divided by what? HA. Are you getting it now? Times how many percent? Times 100%. Is that okay? A minus divided by HA times 100%. Which is still the same thing as, if you look from that Henderson-Hasselbalch equation, this is pH is equals to what? pKa plus what? Log what? A minus all over what? HA. Is that okay? Now from here, they were able to manipulate some equation to get the amount of unionized and the amount of ionized drug. Although these equations, for me, these equations, I'm still having doubt with it anyway. But we are just going to work with it that way. Alright? We are just going to work with it that way. But me, I'm still having doubt with how they actually came about this equation, because from what I can see here, alright, let's leave it. So that is that. Now let's see. The equation they gave to us are to calculate the percentage of unionized, the percentage ionized. What you do, it becomes 100 all over 1 plus the antilog of pKa minus pH. Now, this one is for when you are talking about HA drugs. Now, what are HA drugs? You are talking about acidic drug. Is that okay? This one is whenever you are talking about acidic drug. Now, how about for acidic drug too? Let me just make it so explicit. It's still the same thing I'm doing. So we are going to say for HA drug that is acidic drugs. This is what you do. To calculate the percentage of ionized product, this will be 100 all over 1 plus 10 raised to the power of pKa minus pH to calculate the percentage of ionized drugs. Is that okay? All right. Now that you have known this, the next one is the next one is percentage of unionized drug. I'm trying to think of way to actually prove this formula, but time no even day. Let's just memorize it. Percentage unionized for acidic drug will be still the same 100. Please take note. Don't go and make this silly mistake. But the difference now will now be pH minus what? pKa. Is that okay? So you have pH minus what? pKa. This is the only difference for acidic drugs. Now, I'm going to show you how you will be able to identify between an acidic drug and a basic drug later. Now, the next thing is for basic drugs, it's just like the opposite of acidic drug, basic drugs. That is BH. Whenever you see that the drug is BH, it's still the same approach, but just the opposite. Percentage ionized now, for this one, will now be equals to 100 divided by 1 plus 10. 10 is the antilog. This one now, the first thing that will come up now will now pH divided by what? pKa. So it's just like the opposite of what? Those of the acid. You know, those of the acid, percentage ionized, we say pKa minus pH. Those of base, percentage ionized is pH minus pKa. Then, percentage unionized would be 100 divided by 1 plus 10 pKa minus pH. Is that okay? So these are the various formulas that you should note. All right. So we are on track. Now the next thing is, how do you identify if the question, because they will not give you the question is acidic, or use acidic equation or basic equation. Now listen. All drugs that have pKa, all drugs that have pKa less than 2 are acidic. All drugs that have pKa between 4 to 6 are weak acid and very weak base. Very weak base. So you can also classify those ones that have pKa between 4 to 6 as what? Weak acids. Is that okay? So you take them as what? Weak acid. So anyone that has pKa within 2 to 6, you take them as what? Weak acid. Is that okay? From pKa 2, less than 2 to 6 is weak acid. Now, pKa of 8, of course, you know, 7 is neutrality, right? So we start from 8 to 10 is a weak base and a very weak acid. So if you classify it as a weak base and a very weak acid, what does it mean? Where does it stand? It stands as a weak base, right? Now, all those that have pKa greater than or equal to 12 let's say greater than 12, they are what? Very basic. Are you getting it now? No acidic property. Now, the general rule of thumb is that as the pKa increases, basicity does what? Increases. Are you getting it now? So the higher the pKa, the more basic a drug is. The lower the pKa, the more acidic a drug is. So drugs that have lower pKa are more acidic than drugs that have high pKa. Is that okay? Drugs that have high pKa are known as what? Basic drugs. Now, armed with this knowledge, let's now solve this question. The question says, calculate the percentage of aspirin. Every one of us know here that aspirin is a what? A weak acid. Acetylsalicylic acid, as the name is. That will be ionized, that will be in the ionized form in the stomach after oral administration of 300 milligram. Now, how do you now ascertain, first of all, if the compound, they actually want you to use the acidic formula or the basic formula? You know, we have two formula. One is acidic, one is what? Basic. So how do you identify the acidic formula? The one that will have acidic formula. All those ones that have pKa from around 1 to 6, I told you, take them as what? Acidic. Is that okay? From 0, in fact, if any pKa of 0, because we said less than 2. Less than 2 is to 6 is what? Acidic. Although 6 is weakly acidic. Is that okay? So when we see pKa of 3.5 here, what information does that give to us? It tells us that we are going to use what? The formula for what? HA drugs, right? And then percentage ionized for HA drugs. What do you say the formula is? Percentage ionized for HA drug will be what? 100 divided by what? 1 plus 10 raised to the power of what? pKa minus pH. Abi? So that at the end of the day, this gives us 100 divided by 1 plus 10 raised to the power of. What is the pKa of aspirin? Now, this pH is the pH of the body fluid or the environment that you're actually considering. Now, in this case, it is the stomach. I know stomach is very, very what? Acidic. That is why the pH is high. Low. The lower the pH, the more acidic it is. Now, so this becomes 10. pKa in this case is what? 3.5. So we have 3.5 minus 1.4. And this is going to give us what? 100 divided by 1 plus 10 raised to the power of 3.5 minus 1.4. That will give us 2.1. But let's just check with the calculator. 2.1. Right? Let's just check with the calculator. So 3.5 minus 1.4, 2.1. So you are going to have raised to the power of what? 2.1. So this gives us 100 divided by 1 plus 10 raised to the power of 2.1. What did it give to us? Give us 125. Is that okay? 125. Now, at the end of the day, what do we have? If we take this one to this side, it becomes 100 divided by 125 plus 1 will give us what? 126. So this will be 100 divided by 126. What did that give to us? Okay, this is not just 125. They have fraction. There is 10 to the power of 2.1. 125.89. So this one will be 126.89. So we have 100 divided by 126.89, which is 0.78%. So it means this drug, the ionized form in the stomach, will be 0.78%. Is that okay? Now, how about the unionized form? Percentage unionized. What do you think that will now be? Now, how do we calculate the percentage unionized? Ionized is 0.78. Of course, unionized will be 100 minus 0.78, abi? But then, let's see. From the formula, we say for HA drugs, to get the percentage unionized, what is it? The formula is percentage. I'm just doing this. They didn't ask you to calculate it, but in case, unionized will be 100 divided by 1 plus 10 raised to the power of pH minus pKa. Abina, which is equals to 100 divided by 1 plus pH, 10 raised to the power of pH is 1.4 minus 3.5 equals to 100 raised to the power of 1, 10 raised minus 2.1. And then at the end of the day, this is going to give us 100 divided by 1 plus 10 raised to the power of minus 2. This will give us 0.007943. Now, 100, when this one adds to that, it's going to give us 1.007943, which will be equal to 100 divided by 1.007943, which is what? 99.92%. This is the amount of unionized aspirin in the stomach. Is that okay? Good. So that is that for this one. We'll see in the next one.